All right, so to everyone who's going to be attending or watching on YouTube, welcome to our webinar. This is the fourth in our series of webinars. Our topic today is intrinsic safety, a very important topic, and we have a really, I think, great panel of people here to talk about the subject. So I guess the first thing we would like to do is to start to introduce our panelists here. As we start with Shane, and then we'll go clockwise around the.
Okay. Hey, I'm Shane Filer. I'm with Neil Systems, general manager here, and I've been with the company for about 20 years. I've been in the industry over 25 years now, and quite a bit of that has been involved with hazardous areas, and the chance to teach at like ICA events and other events related to this has been fun. It's a real exciting topic, so I'm looking forward to be part of this today.
Okay, Ed.
Hi everyone, I'm Ed Beardshaw and I work for XLOC Instruments Inc., based down in the Houston area in Texas. I've been with XLOC about 10 years as a VP of Sales and Marketing. I've been in the hazardous area, electronic protection industry for nearly 20 years now. So many years. I really enjoy working on the different applications and helping customers to put systems and solutions together. That's me.
Peter.
Hi, Peter McMenamin. I'm with Gale, and I'm the Northeast sales manager for Gale. And primarily what Gale does is for liquid transfers, we do grounding and bonding equipment that's basically meets worldwide approvals and is for the bulk of the material is intrinsically safe signals operating in hazardous areas.
And Dave?
My name is David Stick. I'm Vice President of Product Chemical Solutions. I'm here about 19 years, going on 20 shortly. Involved with bulk storage, hazard environment. Very familiar with intrinsically safe equipment. Also prior, I had 23 years in the nuclear Navy business as a mechanical engineer and manufacturing engineer.
And most of the people watching will know that I am Joe Stevenson of ICA Engineering. We're a control system integrator located in Union Township, New Jersey, in Union County, because there's 2 Union Townships in New Jersey. So we use both Shane and Ed's products, and Dave has used Peter's products. Actually, all in Dave's facility. So that's why we wanted to have Dave here, because he's an end user. We've been ICA has been in business since 2009. I personally have been dealing with intrinsically safe for about 20 years, and many of our clients have at least one hazardous area in their facility, and so intrinsic safety is something that we're very familiar with. So what we'd like to do is we're going to kind of go through, just to give everybody a rundown. We're going to talk first about some definitions, so people who are watching and aren't familiar can kind of understand some of the terms and the classifications. Then we'll do a kind of breakdown into the different methods, and in addition to intrinsic safety, or a few other methods that are used to deal with hazardous areas. Then we'll get into the nitty-gritty of hazardous areas. We'll kind of breakdown of what it is. And how it's classified. We'll get into a brief history of it, and then we'll show some examples, and then we'll get into some historical disasters that happened where intrinsic safety may have been able to make a difference. So we'll get that kicked off here, and I'm going to start the slideshow, and I'll go in and out of the slides as we go, so people can talk and have their input in there. So let me see here. All right. So again, as Rosalie said, the title of this webinar is the benefits of intrinsic safety technology. As you see here, here's the slides. We got Shane, myself, Ed, Peter, and Dave. And so first thing we're going to cover are a few terms. It's some stuff that's important to understand. what is a hazardous location? Now, some of these slides were created by Shane. Some of them were from Ed. So we've got those marked on here. I don't know, Shane, if you want to kind of go over this real quick.
Sure. Yeah, so if you're watching this, you obviously have an interest in hazardous areas of some sort as defined by a place where an explosion can occur. And so if you look at how a lot of these are rated, which again, if you're watching this, you probably have in your plant or you're involved in some way. So we're looking for an area that can contain some sort of a concentration of, almost always it's gas, but oftentimes we get into some vapors, dusts, some what we call fibers and flyings as well. And we're looking for a situation where an electrical or thermal, a high temperature could cause an explosion if those things were present. And so they're always identified by typically what's possible that could be present, what's the type of risk as far as how much it could be there. Those sorts of things are how we tend to define that.
Right, and there are several different types of hazards. So as Shane mentioned, typically there's gas, vapor, and dust. And we can see there are three things that are needed in order to create a hazard. So there's energy, air, and fuel. So Shane, you want to talk about that a little bit, and then go down to Ed and Peter?
Yep. So, this ignition triangle, if any of you spent any time earlier in your life with the Girl Scouts or Boy Scouts, you probably are familiar with this when they taught you how to start a fire. And I just heard another incident this morning of a North Jersey food and beverage facility that had this exact situation occur. They had a bunch of propane tanks that were mounted on top of a source that caught fire, and then that caused an explosion there and burned half the plant down. So this ignition triangle, it happens regularly at plants all over the place in the US, unfortunately. And often we have to consider, how do we protect from these three things coming together in some sort of an explosive type of a situation?
Ed, you have anything to
add? Not really on this slide. Should we move on to the next slide? Or?
Right, so here's where we get into different types of hazards are broken down into different types of classifications. Class 1 is for gas and vapor. Class 2 is for dust and powder, and class 3 is for fibers and flyings. I'm not familiar with what flyings are actually.
So you'd see flyings if you had like metal shavings, and you had things that could potentially be very, very tiny conductors floating around in the air. That's kind of what flyings are. It's rare that you see it, but in certain applications where there could be small metal flyings, it is a hazard, believe it or not.
Yeah, one of the things that I think that a lot of people don't understand is that it's pretty obvious, the gas and vapors, everyone can think about that. You think of gasoline or propane or something like that, and hitting an ignition source. It's in all the movies, but a lot of people don't think about how dust and powders can create it, or fibers. That they, the buildup in a lot of cases of static electricity can cause a detonation. And I mentioned yesterday in the practice session that they're thinking now that the Lusitania, when it got hit by the torpedo, it wasn't the torpedo that actually destroyed the ship. It was the discharge of static electricity caused by coal dust, because the ship was near the end of its voyage, and the coal storage was close to empty, and that secondary explosion is actually what destroyed the ship.
There's also a surprisingly large amount of materials you wouldn't expect to be classed as hazardous. Like, take example in the food and beverage market. All you got to do is, as an example, put a dusting of pepper on your hand, and over a naked flame like a candle, blow that, and you'll see it burn and crackle in the air. So there's many different materials that you would not expect. Sugar being another large potential hazard in the industry, you've got to protect against.
Yeah, that was a surprising one when I first read it. But of course, if you think about what sugar is, it's a big hydrocarbon, and so it is fuel. It really is a fuel. That's what our bodies use it for, right? The other thing about, once you get into the different types of hazards, you get into then the divisions. And Shane, you want to discuss that?
Yeah, so again, I think this is something that a lot of people are familiar with. Here in the States, we use something called divisions. Over in Europe and other parts of the world, they use something called zones. Very, very similar. But essentially, we define the risk of a specific area based upon its class, its division, its group, and then a temperature, a thermal aspect of some sort. And so the main things to be aware of is the class defines, is it a gas? Is it a dust? What is it? The division or the zone will define how much time is present in a given year that you might see that particular thing be there. So the big difference between Div 1 and Div 2, really Div 1 is we expect it to be there above a certain quantity of time. Div 2, there has to be something that has gone wrong for it to be present. Typically 1% or less of the time we would expect it to be there. And then groups A, B, C, D define the type of gas or the type of thing that could be there. So like a group A is the most dangerous, which would be like an acetylene type of a situation, whereas a group D is a little less dangerous, still explosive, but a little less dangerous, a little less potential to have an explosion.
My particular plant, the bulk tank storage area, we have an adjacent drum-off area. So we just have a roofed area. It's not enclosed due to the fire regulations in New York. And that's class 1, division 1 is that area. We have like a 50-foot boundary there where things are treated differently because we're actually dissipating fumes, flammable fumes. All my storage areas are within closed garage doors. They're adjacent to that, and that's division 2. But to manage the facility, I manage everything with the mindset, everything is division 1, just for those reasons, because once you have 2 things to be concerned about mentally and trying to manage the individuals, it's too difficult and it creates confusion. So you just live on class 1, division 1. And I just, it's sleep at night program, you just can rest of these.
But yeah,
Dave,
that's a good.
Dave, I was just going to say, I would add that that's one of the things that I really try to teach people is the importance of thinking that way, because all too often there's been a huge push over the last 20 years, especially with insurance companies giving you higher rates if you have more Div 1 areas. There's been a huge push toward Div 2, but all too often when we've seen explosions occur, it's in the Div 2 areas where people didn't take it as seriously that the risk could happen. But if it's 1% of the time, that still could be multiple times a year that it shows up. And so I think it's a far safer way to think of everything as Div 1 in what you're saying, Dave.
And that's especially important in a large facility where you may have electrical lines or pipes or whatever that are actually moving from one classified area to another. And so it's very easy if you aren't considering those boundaries that you could end up introducing a hazard that you didn't expect. Plus the fact that just because something is not normally expected to be in an area doesn't mean that it won't be there. And so if you are designed for the more the more likely event, then you have a better chance of dealing with a transient situation that comes up that was not required under the code. And this is the other good thing too is that when you classify areas, it's also good to get your insurance company involved so that they agree and as you said, it could actually bring your rates down if you've demonstrated that you are taking safety very seriously.
Just to add to Dave's philosophy there on site with being belt and braces when it comes to safety, it's particularly important in the world we live in when it comes to mobility that we're seeing in the process industry. So there's a massive movement at the moment for digital mobile workers, if you like. So there's likes of intrinsically safe smartphones and tablet PCs and other equipment. There's even head-mounted wearable tablets that you can do hands-free video calling and video collaboration. So the nature of those products, they're portable, they're mobile, they can go from one area of the plant. So if you don't specify them and rate them correctly for the whole plant, they can inadvertently end up inside a Division 1 when they might only be Division 2 rated. So yeah, it's a big part of what we do now, providing mobility solutions for hazardous areas, and we always do try and look at what's the worst case scenario on site, and let's design from there just to be absolutely safe.
Right, and that's something we'll get into a little bit later. Actually, a project that we did for Dave last year in his drum off area, where we used both products that Ed have and also that Shane had to for a system upgrade, and we'll talk about some of the advantages there. It saved a lot of money in the implementation in the long run, and also added a lot of flexibility that you wouldn't normally have. We're going to move next part of this. We're going to talk about, so now we've kind of identified the things that can go wrong, or what things that can cause problems. The next is the various methods of protection. So we're going to discuss the ones other than intrinsic safety first briefly, just to kind of give you an idea of what else is out there, and then we'll get into intrinsic safety and as to why it is a preferred method. Let me see here. Now I'll share my screen. Okay, so methods of protection. All right, and Shane, you want to hit this one?
Yeah, sure. So we showed this energy triangle earlier as to those three things that have to come together to cause some sort of a spark explosion to occur. And so there's three basic ways that we are going to deal with making sure that those things don't create a bigger problem of some sort. So we're either going to try to contain anything that might occur, we're going to try to segregate things from each other, or we're just going to try to prevent, even if they are together, prevent it from being bad enough to cause an actual explosion. So if we go to the next slide, we'll talk first about just some of the definitions here that you might see. So the most common one that is used here in the States, although not most common worldwide, but here in the States, is explosion proof. And so I'd say probably in 80 to 90% of the plants that have Div 1 and Div 2 areas, we see explosion proof being used in some way. It's popular, it's fairly well understood. And so that's why in the States, it's just something that we tend to use a lot. If you have large panels where you need higher voltages, if you have motors that are high voltage and they need to be used in a hazardous area, purging and pressurization is quite popular. It's a very used thing here in the States. And then certainly non-incentive, I'd say in the last 20 years has become more and more popular as people are looking for ways to I think save a little bit of money on some of the different challenges that are posed by explosion proof, intrinsic safety, things like that. And so non-incentive uses sort of a combination of different ideas and concepts in order to try to prevent a situation from occurring where they use more of the spacing and signage and different things. So we'll touch base on all those. And the last is intrinsic safety that we certainly want to talk about today. So.
Yep. Yep. Now one of the so we go into explosion proof, and the thing that's interesting to me is that there's a lot of misconceptions about what explosion proof actually means. A lot of people think explosion proof, it sounds like it's proof against explosions, that it would basically prevent an explosion from happening, but that's not really what it is it? Shane? Ed?
Yep. Sorry, I'll let Ed go. I've been talking a lot. Go ahead, Ed.
Yeah, you have a break. Yeah, you're absolutely right. So the idea behind it is that this is where the containment comes in. So you can have equipment that isn't certified or rated to be installed in a hazardous area can go inside an explosion-proof enclosure. And you can have an explosive atmosphere inside the enclosure. So that's a mixture of gas or dust and air. And so the enclosures themselves are designed and built in a way that they're very mechanically protected and built to withstand an explosion which could happen inside. And so around the edge of the enclosure, where you see the numerous bolts that hold the lid onto the base, that is designed to a specific specification, and that's what's known as the flame path. So that has got to be a certain minimum distance so that if there is an explosion, inside that enclosure, it is contained, and that flame of the fire essentially does not propagate out into the external environment.
Right. Yeah, that's the thing that I found interesting, that it really means that you're going to contain an explosion. It just doesn't at all prevent one.
No.
And so the name is a little misleading, because you would think that it would stop an explosion, but it doesn't. Okay.
Also, the way these devices are manufactured, they're manufactured like with a flatness of 1,000th of an inch. So when you bolt it up and you secure that, that also eliminates not only explosion from being exerted from the device, it also prevents flammable fumes from entering the device with electronics on.
Right. Okay.
One thing, if you can stay on that slide just a second there, Joe. One fun thing when I teach, I like to ask the question, just to say, have you ever had one of these panels, as you see here, where you've seen that people have sawed off the bolts and super glued them on, or just had the corner ones on and forgotten all the rest of the others? And, have you ever had the conduits, what they fed into there, not filled correctly? And almost everybody kind of does the, look around at each other, and then they all sort of, raise the hand slowly, because they've all seen it at their plants. And so, it is something, I think, that because there isn't a good enough teaching on some of this, they end up causing other problems. So it is an issue that you got to worry about.
Right. I mean, that's the thing, is that it has to be it's definitely a maintenance issue, because if you do have to access these locations, there's a lot of hoops you have to jump through. Whether it be a chemical sniffer or shutting down power to the area. So a number of precautions you have to take, and people tend to, very often will cut corners, because it takes a lot of time to unbolt something with 40 bolts. So you end up with a situation that may have started out safe, but over time ends up becoming unsafe. So next one we have here is segregation. And so as you see here, this is pressurization and purging. Typically on control panels, you'll see a purge. There's a few different types of purges depending on what the hazardous environment is. But basically what it does is it forces either air or nitrogen into the enclosure to create a positive pressure to prevent vapors and gases and dust and so forth from intruding into the panel, which there's some that provides many challenges of its own. For one, you have to measure the pressure, and you have to make sure that the pressure is maintained. If the pressure is lost, you generally, depending on the area classification, you may actually have to cut power to the box, because if you don't have that positive pressure, then you no longer have any protection. Depending on the equipment you have inside, you may not have to do that, but even there, but you have these purge kits, and purge kits are relatively expensive. The cheapest one that I've ever seen is like $3,000 to $4,000, and I've seen them as expensive as $15,000, and I'm sure they go even higher than that for something that requires large volume. So it's actually Dave, you have a purge panel out on the loading area.
We have two of them. Yeah, two of them in the area. The blending tanks, that project we do with you, and then the drum filler house. Right.
And that's the thing. So when that facility was designed, there was not the intrinsic safety was not apparently considered, or wasn't aware of at the time. So you end up with a purge panel. Now, there, part of the issue too is that you have a touch screen out there, and so that had to be in the purge box, and it had to be behind behind glass, so
it could be within that pressurized envelope, so.
Right, that's right.
And then you have your main electronics, your 220 or whatever the high voltage is. That's an explosion proof metal contained area. This is a NEMA-4 enclosure with pressurization inside. So
right.
They kind of work hand in hand, so.
Sometimes it's just not possible to use another form of explosion protections, but so purge comes in when you're dealing with high power, drives or motors, or even some sampling systems, analyzer systems, where you've got the nature of the design of the system, you've got an internal source of release potentially in the panel, because you're bringing in a sample from the process. So you need to maintain that positive pressure inside to make sure there's not a flammable gas air mixture in there for an explosion to happen.
All right. And then the next method we have is non-incentive.
Yep. So the one thing with non-incentive, again, it's become much more popular in the last 20 years as people have had this effort to try to move to a Div 2 sort of environment and to cut some of the costs associated with the explosion-proof purging, intrinsic safety methods. And it's a little bit of a conglomeration of a few different methods. So it's kind of similar to intrinsic safety in some ways with things we'll talk about. But it's more of a focus on sort of good practice. They'll put some signage up to warn people that there's something here that could be dangerous. They'll do hermetically sealed contacts to prevent a sparking type situation. They'll have certain rules that they'll follow from one method or another. So it is a bit of a conglomeration. It can certainly work fine. But it's more of a risk minimization than it is as much of a safety method like intrinsic safety or some of the others. But it is incredibly popular and has grown so over the past 20 years.
Yeah, this is something we see in integration. I see a lot. Probably the most common for me is actually keyboards. Sometimes if you can't put a touch screen in a location, then one of the other things to do is to put in a keyboard. And so there are a number of makers who make non-incentive keyboards because you just can't put a standard keyboard out there in the hazardous area because of the potential for a spark.
I think non-incentive also has uses in the mobility world due to the design specifications that you can use to meet the certification requirements. You don't have to use costly, heavy explosion-proof housings for the equipment. And again, it's only really designed for Division 2, not Division 1. So it does have its uses for sure in the mobility world.
All right, and that of course brings us to the last one is intrinsic safety. Last but definitely not least, and this is all about preventing a spark from occurring. If you don't have an ignition source, even if you've got the air and the fuel, if there's no ignition source, then you can't create an explosion. And this is what that's all about. And you can see here, there's we see some Zener barriers there that we'll get into in a little bit. But the idea is that you segregate your equipment from energy sources that would produce enough power that could cause a spark. Anything else?
Yeah, if you jump into that next slide, I'll walk through a few things for you there. So, one of the things we get asked a lot about intrinsic safety, we provide for a company called MTL, barriers and isolators. And one of the things that we probably get asked the most is, hey, I've got this transmitter and I want to make it intrinsically safe. What do I need to do? And so one of the things that we really try to teach people is that intrinsic safety is not just adding in a barrier or isolator, it's an actual system. So it's a system that includes the barrier itself, it includes the wiring, it includes the device that's in the field of some sort, and the whole idea of it, with that whole system in mind, is we're going to make sure that we never have a temperature that can cause a problem, and we never have a possibility that an ignition source makes its way out into the field that could cause a problem, nor could build up enough energy in the field to cause a problem as well. So it's an entire system that has to be thought of. And so certainly of all the methods, this one requires kind of the most electrical engineering mindset to be thought through. So
Right, that's the thing. Yeah, you can't just take your standard transmitter and turn it into intrinsically safe if it's not rated for that.
Right.
And that does create some design challenges that we'll get into. So as Shane said, there's temperature ignition, panel source ignition, and buildup of electrical energy. The good part is that intrinsic safety will work with all classes, all divisions and zones, and it's the only solution approved for Zone 0. So Zone 0 is a European zone. Basically, their Zone 0 and Zone 1 is collectively equivalent to our Division 1. But they've kind of broken it down into a little more detail, and it's the only solution available for that. So this is the reason why it's intrinsic safety is used quite a lot in Europe. It's not used as much here, but it is growing in popularity.
So
Sorry, go ahead.
it's also possible, Joe, that you have an explosion-proof rated device in a Class 1 area that has contact outputs that would not be able to control something in that Class 1 environment unless it was intrinsically safe. Say a pump start or a solenoid of some type. So generally they'd have to pipe out of that divisional classification and then take a signal back in, unless there's some type of barrier or intrinsically safe signal that comes from that device.
That's a good point. And real quick, just one little note that's on the slide here is that it also works with any wiring practice, whereas explosion-proof requires, for instance, rigid conduit and certain types of seals and everything like that, certain type of unions and connectors, and you don't have the same level of requirements when it comes to use intrinsic safety. So where did intrinsic safety come from? Why, how and why was it developed? So we get into that. It came out of the coal industry. Ed, you want to cover these? Your slides?
Yeah, sure. So that's pretty dark history, unfortunately. But back in the early 1900s in the UK, probably not just in the UK, I'm sure it was something that happened all over the world where there was coal mining. But in the UK, coal mining was very prevalent at that time. There were, as you can see, a lot of significant disasters that occurred, where many hundreds of people died, unfortunately, from explosions that occurred in the coal mining industry. Unfortunately, intrinsic safety came about from an investigation into one of the largest disasters, which was the Llangennid colliery in Wales, which was in 1913. And we can go on to that. Yeah. So what happened? This slide just shows a basic. It's a representation of what they used to have in the coal mines. It's a winch signaling system. So just to explain what you've got here, you've got a circuit here consisting of old batteries, jam jar batteries here. And you've got two bare wires that would run out into the shaft and through into the mine. And when the miner within the shaft was ready to for the winch operator to bring back the coal and the carriages, he would short out the circuit by shorting out those two wires, and that would then energize the bell to ring. So that was a rudimentary signaling system that was widely used. And what happened specifically on that day in 1913, 400 people died. The investigation found was that as the mine was going deeper and deeper, the cables obviously had to get longer and longer for the signaling system. And due to the volt drop in the circuit for the extra cable, they had to add more and more batteries. And so it got to a point where the energy within the circuit met the minimum minimum ignition energy required to ignite the flammable gas air mixture, which was down in the shaft. It was methane, natural gas. So yeah, the investigation found that there's different gases have got different minimum ignition energy limits. So unfortunately, at that day, they met the threshold for methane, and that caused the ignition and caused a huge explosion. which obviously killed a lot of people.
Right. And what I want to do too, I want to jump back one slide for a second. To just the added potential dangers in a coal mine is not only did you have the methane gas, but you also had coal dust, which could also cause detonations as well. And so then, again, this is another one of those things where, I've been in some facilities where they're using fibrous material, and you're not necessarily seeing proper grounding or anything like that. So because grounding, and Peter, if you want to talk about this, grounding is a method of dissipating energy that builds up, whether it's static energy or some other type of energy.
Yeah, a couple of things. One is, everything we're talking about sounds like it takes a lot of energy, but it doesn't, right? So a typical static spark just from your finger that you might see while you're taking clothes out of the dryer are enough to ignite methanol because of its low, ignition energy as a source. So not all materials meet that, but, safety practices would kind of state, we're going to play for the worst, right? So what we do is we carry an intrinsically safe 2-wire clamp to, say, the top of a 50-gallon drum or someplace where there's gases escaping from a transfer. And we want to keep those items while they're doing a transfer neutral, right? So we're going to ground the drum, we'll ground the lance. That signal to that clamp is 2-wire intrinsically safe, and it provides a green light when you clamp properly and meet a less than 10 ohm threshold, which is required by National Fire Protection. NFPA 77 says if you're grounding something for static, it should be at less than 10 ohms. Most wires are way less than 10 ohms, right? They're a short circuit. But the important part is if you latch onto something and you don't penetrate properly, you don't make good contact, you won't provide a current path for that intrinsic safe signal, and it won't tell you, it won't give you a green light. It'll basically say you've got to reposition that clamp so that you make good contact and ensure that it's grounded. So when the resistance is over 10, it's more important to know that.
Right. So now I've used systems like that before in the past. I remember one particular one was a bulk truck operations, very similar to what Dave is doing. And we were bringing those signals into our controller. And then based on whether or not there was a good ground, we would enable or disable pumping. So if we weren't getting feedback from the grounding system that said we have a positive ground and everything's working correctly, we would not allow the chemical valve to open up. We wouldn't allow the pump to start, so they could not transfer material until they had a good ground. Because of course, if we allowed them to move forward, then there was potential for hazard for detonation. So this is how a lot of these different devices kind of work in tandem with one another. So it's as Shane was saying before, it's a system. It's not just a matter of getting the signals in, but now what do you do with them? And that becomes a big design consideration. Is once if you is detecting when your safety system is no longer or your system or the area operation is no longer safe, and then what do you do to prevent that ignition from happening or the fuel from being present or whatever?
That's pretty much how my plant is set up as well. If the tanker's not grounded properly, you don't get a green light. It disables the electronics and the 220 voltage, which is explosion-proof equipment. Quick story: there was a bulk chemical storage plant that I was reviewing. I used it for training, but they were loading material. Humidity was bad. It was just like the perfect storm. The truck was grounded, allowed to dissipate for a half hour before loading, and they had a stainless steel filtration canister that they used that was grounded, had polyethylene 1 micron filter bags in it. The operator decided that particular day that he didn't want to remove all the bolts and everything to change out the filters, so he put a bag filter on the other end of the lance that's doing the loading on the loading arm, and he zip tied it to the bottom of the lance. Although the tanker was grounded and properly stored, the polyethylene bag contained energy. Being non-conductive, it was loaded in as soon as he started the pump. It was a methyl acetate 30-degree flash point. The tanker went up. And thank God the tank farm didn't go up, but it was a pretty severe accident, and it was a wake-up call. But after a forensic investigation, we saw the only thing that was left was the zip tie, and we questioned it. And the grounding light was green. Everything was done properly. You know, once the fire was put out, but it showed, and he admitted that he put a filter bag on the bottom of the lance. So the energy in the filter bag, as soon as it made contact with the fluid coming out of the lance, discharged and tried to ground itself to the fluid.
Right. And so that's the thing. So that's goes. Not only do you need to have the right equipment, but you also need to have the right procedures in place. People need to follow. You need to set up a regimen of rules, and people need to follow those rules. And and there really is there's no room for error. We're going to move on to the next section. Talk about the components of intrinsic safety. All right. So generally speaking, and we'll go into more detail about this, but you have your intrinsically safe device that's in the hazardous area. So whether it's gas, dust, or filings or whatever, you've got your device that's there. As we've mentioned before, it has to be rated for intrinsically safe. And then those signals are brought back to the safe area. And I noticed there's a sealed separation. So wherever you have a penetration from a hazardous area to the safe area, there has to be sealing. It has to be sealed so that there's no possible penetration of the hazardous substance into the safe area. And then you'll run that through an intrinsically safe barrier or isolator, and then that signal goes to your control equipment. So the barrier or isolator provides that isolation between the hazardous area and the safe area. And this goes to there's a couple different types. Shane, you want to talk about these? These are yours.
Yep. So just to be quick, all of us probably have heard the term Zener barrier and galvanic isolator, but there is a big difference between them. With the Zener barriers, they're essentially using something called a Zener diode, as well as a resistor and a fuse, and sometimes multiple components of those just for extra safety. But it's to make sure that if we ever have a situation where too much voltage is trying to come down the path out to the unsafe area, the hazardous area, the Zener diode will drop that to ground. And so it needs to have a very, what we call an intrinsically safe ground, less than 1 ohm between the barrier ground and the actual plant ground. But then there's also a resistor, so we don't ever have a situation where we could have an overcurrent situation. And there's also a fuse, so we don't have a situation in the field that could ever cause the barrier to be stressed as well. So we're really hitting it from 3 angles, and so it gives a lot of extra protection there. The galvanic isolator, on the other hand, there's no need for that intrinsically safe ground. It specifically creates essentially an air barrier because it's almost like a transformer where it's creating an actual separation with a galvanic isolation between the hazardous area and the safe area. So 2 different methods to do it. Generally, barriers are much cheaper, but require a little bit more electrical engineering to get it right. Isolators cover over a load of sins, but they typically cost about 2 to 3 times more.
Yeah, and just as ICA, we have a tendency to go toward the barriers, particularly in a retrofit, because if the overall plant and the systems were not designed to provide that earth and all the other things that you need, it's a simpler installation, even if it does cost a little bit more. And so, yeah, basically there's 2 different types of intrinsically safe devices. There's the simple apparatus. You want to talk about that, Shane, again? This year's
simple apparatus would be something that will never be able to either store or generate too much of an electric type ignition that could cause a problem. So you're talking about typically thermocouples, some buttons, switches, LED lights. Those sorts of things are all simple, meaning that they don't have to be approved to be intrinsic safe. You could just go with an off-the-shelf unit and then apply an intrinsically safe barrier or isolator to it, and that would make the system be intrinsically safe. That is not true, though, when it comes to other things like transmitters, other types of lights, Certain other things have to be approved and tested that they can't electrically or thermally cause an ignition situation to occur. So they must have the approval by an approval body that says, this is an intrinsically safe transmitter, as an example, and it must be combined with a barrier isolator and the right calculations for the cable to make sure that the system as a whole in total is an IS system.
Right. And benefits and challenges. Since we're a little short on time, I mean, we'll just run through this quickly. As you mentioned, the intrinsic safety is good for all divisions and zones. It is the safest of all methods because it prevents detonation from happening, whereas the others work on containment or segregation. You can, if you're using intrinsic safety, you're allowed to do hot work in the area without needing a chemical sniffer. And as I mentioned before, the wiring is easiest. Now, there are some challenges. As Shane mentioned, there are some calculations you have to do because since it is a system and not just a device that's required. So it takes a little bit more work, and that's where companies like mine, like ICA, and we would work with a company like Neil Systems to work that out, or with Ed over at XLOC picking the right devices. And it is limited to low voltage. So if it's something like AC voltage, then you can't do intrinsic safety. You have to do something else. But what more and more we're finding that the preferred design from a lot of our end users is 24 volt anyway. People are trying to get away from AC because it does create a lot of issues. That whenever possible, we're going with the low voltage systems. And UNS have the low resistance path to ground. Couple play things that have happened in recent years that may have been helped by intrinsic safety. Clean energy systems in 2010. It was a combined cycle gas and oil-fired power plant. They were purging a natural gas line in a blowdown, and this is disputed. Some said that it's a flame device, but there's others that said that it was actually caused by electrical spark, possibly by a improperly protected control panel. The investigation wanted to look to see whether electricity was cut off from the area, whether they had been evacuated before purging, and whether the ignition source were present. There was so much extensive damage, it was hard to tell exactly, but it's likely that intrinsic safety would have been useful in this case. And then the next was the Wesco grain silo explosion, 1977. This was actually created by a spark igniting grain dust. It's possible with static electricity, in which case systems similar to what Peter was describing would be worked. There are, Peter was talking about ones for vapors, but there are similar systems for dust and powders. And so having that kind of setup could have prevented this accident. Now, just to talk about some applications we've done. So, and this is great because everybody involved is here. For Dave, we had put in a new, we replaced the PLC, and the existing system didn't have a touchscreen, or it did, but rather they couldn't use it as a touchscreen because it was behind glass, because it was a class 1 div 1 area, and there's really very few manufacturers who make class 1 div 1 rated screens. So what we did was the one possibility would have been to get a rather expensive touchscreen, $15,000 to $20,000 installed cost. And instead, we reached out actually to Ed at XLOC, and we ended up getting an intrinsically safe tablet. You want to talk a little bit about that real quick, Ed, while we got time?
Yeah. It's something that's really come about in the last 4 to 5 years. There's been certain manufacturers who've developed class 1, division 1 certified tablet PCs. So similar to your desktop, your laptop, they run Windows 10. So essentially they can be used as a mobile HMI. They have Wi-Fi and Bluetooth. So I think, Joe, what you created was a Wi-Fi link between the tablet with your
Correct.
control system and had some software running natively on the tablet.
Correct. Yeah, Dave had some forethought with his facility and had a Wi-Fi. I don't know if it was XP or IS Wi-Fi put in, but basically we were able to piggyback onto that and then network that back to the PLC. And so now instead of having a fixed terminal, which obviously is only in one spot, and can get very expensive, if you have several spots within a facility that the operators need to operate from, if they've got fixed terminals, that means you're going to have to put a terminal in each location at a very high cost. Whereas for, I mean, the prices vary, but under $5,000, a tablet, compared to 15 to 20,000 for a fixed location, and then the operators can actually walk around the facility and work at different places. And now in Dave's case, where right now we only have the one, but you could conceivably have multiple, if you figure for the price of one fixed station, you can have multiple tablets that can be working in different areas. And there's ways that we can, via software, to actually identify where in the facility the operator is and bring up the appropriate application or screen so that they can work on that. We've actually talked with Dave about that, doing that in the future.
Yeah.
At as one of his other facilities, is that have this context sensitive system that as the operators move around the production areas, that they'd have tablets on the forklifts and then a few others that so as they're moving material around and they're doing various processes, that the operator would have everything right there for them. And again, at a much lower cost than putting in very expensive fixed locations, fixed terminals.
Yeah, so before we used to have the touch screen was behind, we had a toggle on the outside that was explosion proof. They used to manage and you'd pick it and select it. So now we removed all those guts. We put a PLC upstairs in a loft on a non-hazardous area. Because remember, I'm outside, I just have a roof. So the Northeast, I got 20-degree weather to deal with, and they're outside drumming. So in the maintenance, these things would go down. I have to open up the cabinet, secure the area. Now I got, this tablet we carry out there, we charge it inside, we bring it out in the morning. And then I have another setup, the operations manager's office, my office, and then there's 3 locations where if something happened to the tablet, it got dropped or something got damaged, we can operate the drum fill from 3 separate locations in an office environment.
Right. And then now when we first, when we got involved 2014, David added 5 tanks. We actually used MTL barriers, actually isolators, to isolate between the new transmitters that were put in and the PLC. So this way, instead of having again to do that rigid conduit, which would be very expensive, they were able to just do simple EMT and save quite a lot of money on the installation. Way was way less than the cost of the isolators.
Yeah.
So do we have any questions from the attendees?
Yes, we do.
Okay.
The first question is, do you provide education for your customer on the maintenance of their complex apparatus intrinsic safety system?
Yes, we do. We can if depending on what you have, if you either have existing systems or if you need systems installed, we can provide the information, for both us as an integrator, and then if we need additional information, we can bring in people like Ed and Shane or Peter, and we address whatever needs you have. So and the key thing too is really to understand what you have and where you need to get to, because the answer as to what the solutions are will be very dependent on where you want to get to. So if we know what you have, where you are and where you need to be, we can come up with a long-term strategy so you can roll these things in, whether it's on a project basis or an ongoing maintenance basis, and also train up your people so that they know what the rules are, because obviously that's important. Like in that case that David mentioned, they had done everything right from a electrical perspective, but then the operator didn't follow procedure correctly, and that still caused a problem. So yes, that's definitely something that we can do. And like I said, and for anything, we know a lot, but whoever we don't know, we have the experts available to bring in and supplement our own knowledge. The next question Is it always better to treat Division 2 as Division 1 if your plan has multiple zones? I guess it depends on your facility, how many areas you have, and if they cross over and things like that. So that the layout is important. It's good to at least think of that, going in, as Shane mentioned, and it's definitely something that you can consider, and at the very least, weigh the two out and run both scenarios and say, okay, this is what's gonna cost, and this is the risks of doing it as segregating, have separate Div 1 and Div 2 areas, and here's the cost and the mitigation of if you do everything to with Division 1 in mind. Particularly if you do have stuff that, if you have any mobile equipment or anything like that goes from the areas, or if you have a lot of lines that cross from one area to another, it's probably a good way to go. Shane, you want to add anything to that?
Yeah, I think that's one, it's a little like asking how much life insurance do I need to buy? Or how much, how protected do I want my house to be with a security system? You could really go all out and spend a lot of money and have a lot of protection, or you could try to say, listen, I've got a limited budget. I want to do what I can to just barely meet the requirement there. So certainly with Div 1 and Div 2 in plants, we see over the last 20 years a huge push to get down to Div 2. So plants are taking their Div 1 locations, they're blowing out walls, they're adding fans with enough air exchanges, everything that they can do to make those areas more safe so that they can become a Div 2 area. And that cuts the insurance costs down for sure. However, when we study accidents, all too often there's a momentum of things that happen. It's not one thing that goes wrong. It's usually one thing and another thing that goes wrong. And so I would certainly say, if you can add extra safety and do what Dave did and think, you know what, I could easily have a scenario where, yes, I'm lowering my risk with Div 2, but I'm not eliminating my risk. It's still Div 2. The risk still could be there. I still could have a problem. I'd rather err on the side of safety so I could sleep better at night. So that's one thing I would definitely encourage.
One other consideration of that too, particularly if you're like, I'm thinking from my perspective, I've got a control panel, and if some of the signals are intrinsically safe and some of them are not, because some of the areas are Div 1 and some of them are Div 2. For one, they have to be segregated within the panel, and then you have to be very cautious about any additional signals that go in to make sure that what gets done correctly. So the one advantage administratively of treating everything as Div 1 is you don't have that problem. You don't run into that issue. Or I've seen we had an issue at one facility where we had things, some were Div 1 and some were Div 2, and so we had the segregated IS signals and non-IS. And then we ran out of IS signals and they wanted to add another device. And then we had to make some significant modifications to the panel in order to accommodate the additional signals, where if everything had been designed for, assuming Div 1, wouldn't have been an issue. So, so sometimes actually there can be extra cost associated with things being separate, having both there, and then designing for both in the same panel. So it really depends, and like Shane said, it depends on how safe you want to be and what your budget is. But always, again, I always say that if you know where you want to be, there's ways to design things such in a way that if you take a more budget conscious method in the short term, that you could at least get yourself to a safer place in the future.
Recommendation: if you have a Division 2 area, such as a package drum and a 55-gallon drum, it's all based on risk basis. Is it going to rupture? Is it going to fall? Is somebody going to damage it? So they basically look at it like, normally in a normal day, everything's safe. We can go to a Division 1, a slightly lower electrical qualification for NFPA 70. But that's really a cost basis thing. You got to look and weigh out your costs, because electrical conduit and those enclosures, it's not going to change. You don't have the human factor. But I would highly recommend, if you have a Division 1 and Division 2 areas, to keep the mindset of the personnel always in key to Division 1.
Yeah, I say I read that too. And also what I've seen, what's happened in the past at some facilities I've seen where because their mindset is built around how do we make things Div 2 or how do we make it less, so it's cheaper, that they end up cutting corners and really kind of fooling themselves. Like the facility I went to where they created what was supposed to be a safe area and we had barriers, and then there was no positive pressure in the safe area. It's in a building that everything's Div 1. There really should have been positive pressure in the room to make the room a true safe area, which they didn't do. And then to make matters worse, they put in an air conditioner that wasn't drawing air from outside, but was drawing air from the hazardous area.
Wow.
So they were literally creating a potential bomb.
Actually moving fumes.
Yeah, so basically the money spent on intrinsic safety was kind of a waste because they were literally bringing hazardous fumes into what's supposed to be a safe area, and they didn't even prepare the safe area right in the first place. So it's really a holistic approach that's necessary. And so the primary goal should be, how do we make ourselves the most safe, and then how do we afford to do that, rather than the other way around. Because if you have the wrong mindset, you're going to get yourself in trouble.
Joe, I'd add to that, one thing I always like to teach people is, if you study the space shuttle explosion back in '86, when they went to the very end to do the full audit of what happened and how they got there, they came away with the fact that they were asking the question backwards, where if you study the whole thing, what was being said was, hey, can you prove to me that it's unsafe to launch? And they said, if they would have only just asked the question in reverse, can you prove to me that it's safe to launch? They wouldn't have launched. And so same thing when you're doing this sort of design here, can you prove to me it's safe to start up my plant, is a very different way of thinking than the other way. Right.
And in Europe, they do seem to have a different mindset. And as a result, intrinsic safety is a lot more popular. Ed, if you want to talk about that, the statistics you gave us yesterday during the test session.
Yeah, we'll do. So yeah, I mean, I'm not sure how many years ago this came from, but in the recent past, I think there was a year where there were 17 explosions across North America, which caused either loss of life or serious injury in the process industries. That same year, in the whole of Europe, there was one. So it shows you, and the producers, the chemical companies and process industry operators, they're dealing with the same materials and the same processes, but the real difference is the adoption of intrinsic safety, which is by far the most popular protection concept used for instrumentation in and across Europe.
That's right. And basically that's grown out of that mindset. So again, they had the right mindset, they ended up using the right technology, and as a result, far fewer explosions, less loss of life, less equipment damage, less loss of product, less loss of business. So that's the other thing that considers, what does it cost to have a serious accident, and that's got to be part of the equation, especially the loss of life or a limb. So I think that well wraps it up. I guess if anybody has any parting comments they want to make, we can do that now. Peter, do you have anything else you want to say before we go?
No, I'm good.
Ed?
No, thank you for having me. I've enjoyed it. It's been a great session.
Okay, Shane?
My only parting thought would just be, for everyone who is watching this or has listened in, it's important to know all the different methods and all the different benefits and pros and cons of each one. The more you know and understand all that sort of stuff, the better decisions that you'll make, I think.
Dave, any parting thoughts?
I'm all good. A pleasure, gentlemen.
All right. Well, I want to thank everybody for showing up. Ed, Shane, Peter, and Dave. Wonderful contributions. We did go over our usual time, but I think it's a very important topic, and I think it's worth the extra time. And there's a lot to cover. There's so much more we could say. We could make this a 3-hour session and still not cover everything. But that's, for anyone who's watching, if you do have questions, you want to reach out to ICA, and we will apply our expertise. And as you can see, we have other experts we can bring in to fill in any gaps and deal with any circumstance you may have, both in the short term and in the long term, and give you a plan long-term plan that will keep you safe. Thanks, everybody.